In this video, we're going to be talking about evaluating our forecasts. In other words, we are trying to see how accurate our forecasts are. And so there are different metrics of forecast accuracy that we will be considering. If we really want to test how well our forecasting models have performed, we always want to use these metrics. So let's take a look at a few things when it comes to doing this type of forecast accuracy. So when you look at your entire data set, let's look at this line over here with blue and red dots. When you look at your entire data set, you typically want to split that data into two parts. The first part being training data. So you want to use the different types of models on your training data and train those models to the patterns in the data set. Typically, a good size for the training data is 80% of the total length of the time series. Okay, and we want to keep about 20% of the time series for testing purposes. So we call that test data. There are a few other names that are used for training and test data. Training data is also called in-sample data, and test data is also called out-of-sample. Now, you might not be thinking that this is out-of-sample. You might be thinking that this is still in-sample, but we're not using the test data for forecasting purposes, okay? At least we're not fitting those models to the test data. We're only fitting those models to training data. So a few things to remember here is that any model that fits the training data well will not necessarily forecast well, okay? You can always try to find a nearly perfect fit by trying to add more and more parameters to the model with more and more data on the right hand side. And so overfitting usually in forecasting doesn't work very well. Okay, so overfitting a model to data is considered to be just as bad as failing to identify systematic patterns in the data. Okay, typically simpler forecasting models outperform more complicated ones. Okay, that's why in this chapter we have introduced these benchmark models. Now, the test set must not be used for any aspect of model development or calculation of forecasts. So forecast accuracy is based solely on the test set. We look at what this actual data is in our test set and we compare our forecasts to that to see how far or what's the deviation of our forecast from the actual data. Now, remember that you want to always distinguish between forecast errors and residuals. Residuals are obtained when you are looking at the difference between your training data and your fitted values. Okay, your fitted values are just one step ahead forecasts, but your forecast errors are obtained when you look at the difference between your observed value of the time series and the forecasted value of the time series. Okay, so if you're thinking about this test data here, we're looking at the difference between the test data, which is the actual data, and the forecasts that we construct. Okay, so in other words, we can write forecast errors in such a way. ET plus H represents the forecast error H periods ahead. Okay, so if H is 1, if we're thinking about one step ahead, H is 1. Okay, and one step ahead forecast error will be equal to the actual value of Y, the first value in our test set, minus the forecasted value, one period ahead. So unlike residuals that are actually one step ahead forecasts, Forecast errors are based on the test set and involve multi-step ahead forecasts. These are actually true forecast errors because the test data is not used in computing the forecasts themselves. Okay. Now, if you think that a model has very well behaved residuals, which are obtained from modeling, that typically is not a reliable indicator of how well your forecasting model will perform. Okay, so that this could be the problem with if someone is trying to overfit the training data and trying to base their forecasting model on just the residuals, then this may or may not perform well. Okay, so what you really want to look at is how well are the forecasts performing relative to the observed values of the time series. Now, notice in this last section here, the forecasts for quarterly beer production are given by those four methods that we know, the benchmark methods. We can see that the drift, the naive, and the mean model, they don't perform as well as the seasonal naive model. Okay, this we can see just by eyeballing, but in many cases we are not able to see that. So we need some sort of a metric that tells us the measures of forecast accuracy. So let's assume that yt plus h is the actual value of the series in the test set. Okay, so h is our forecast horizon, and we are looking at h going from 1 to capital H, which is the max value of the forecast horizon. You have y hat t plus h is your forecast. We're given all the information at time t. Okay. Now the forecast error is computed as this. We've explained this before. Now there are different types of forecast accuracy metrics that we can look at. One is called the mean absolute error. The mean absolute error is just based on what you basically are looking at for each forecasting horizon, where h is 1, 2, 3, and 4. You're measuring those e's, which are forecast errors. And then once you have the e's, you're looking at the absolute values of those e's. So you'll make a column with e's, then the forecast errors, then you'll have the absolute value of the forecast errors, and then you will take the mean of the absolute values of the forecast error and obtain the mean absolute error. So that's in the name itself. It's called MAE in short. The other type is called mean squared error, in which we are going to take those forecast errors, square them, and then take the mean of the squared values. Okay, so we usually don't report MSE, but we actually report RMSE, which is called root mean squared error, because the units of root mean squared error would be the same as the time series itself. Now note that the mean absolute error and the root mean squared error, or the mean squared error, are actually scale dependent, which is to say that if you were measuring something in thousands, then these would be scaled up by 1,000. If you were measuring something in trillions, this would be scaled up by trillions. Okay, so the things might seem large if you're looking at mean absolute error, mean squared error, root mean squared error, but the problem is that these are all scale dependent. So we want to look at something that is more scale independent, and so this brings us to MAPE, which is the mean absolute percentage error, which is given by looking at the ratio of the forecast errors, okay, in the numerator, and taking the absolute value of that, dividing that by the value of the time series itself in the test set, taking the absolute value of that, dividing those, and taking the mean of that ratio for the entire forecast horizon and multiplying that by 100. So this is really just looking at the deviation of the actual value from the forecast divided by the actual values. So the mean absolute percentage error is scale independent, but it is only sensible for values of y that are positive. Okay, so you can't use it for anything that has a 0 in it, any time series. There's another interesting type of forecast accuracy measure that was recently published, well, not so recent, in 2006 in the International Journal of Forecasting by your textbook author and Kohler. This is also scale independent. Instead of dividing the absolute value of your forecast errors by y, t plus h, they instead suggest that you can divide that by q, where q is a stable measure of the scale of the time series yt. So you can read more about that in the book, but really q is just given by looking at the sort of the average values of the difference between two consecutive y's. Okay, but we want to apply all of these, and we want to take a look at what sense can we make out of these forecasting errors when we look at data. So the first thing we're going to look at is training set accuracy. So if we are working with the beer data again, we can try to say that the training data set is just going to be post 2007, and we're going to fit these 4 different types of models to the training training data set. Okay, and you know how to do this, but then we can look at the accuracy of all of these models, but we're not looking at out of sample yet. We're still looking at in sample because we're still working with our training data set. Okay, so what you will get if you use the accuracy function are 4 different types of accuracy metrics. Okay, so the columns are representing 4 different types of accuracy metrics: root mean squared error, mean absolute percentage error, and mean absolute scaled error. And those are given for the 4 different types of methods that you use. Okay, so what we can do is we can compare column wise on different metrics. So if we were to look at root mean squared error, then we would say that in terms of model fit, the lowest root mean squared error would, the model that has the lowest root mean squared error would be the winner. So in this case, if we look at the first column here, the seasonal naive method, which when we eyeballed our forecast also performed best. So the seasonal naive method has the lowest root mean squared error, and that is the winner. Okay, no surprises there. But if you look at other metrics as well, right, the value of the mean absolute error or the mean absolute percentage error is also lowest for the seasonal naive method, and similarly for the last column. So looking at all metrics, the seasonal naive method is the winner, which was pretty obvious for us before. But what we are actually interested in is the testing set accuracy. So we want to look at what happens if we actually forecast using our test set. So we forecast using our different models, okay, which are contained in beer underscore fit, and we forecast 10 periods ahead. Okay, this forecast horizon can vary, but in this case, this is quarterly production, so we're looking at 10 quarters ahead. And we can then use the accuracy command to see how the forecasts perform relative to the actual data in our test set. So when you're looking at test set accuracy, the important thing is to give two arguments in the accuracy function. The first one being the forecasts themselves, which is beer underscore forecast. And the second argument here would be the value of the test set, or this is your test set, recent production, or the actual values, I should say. R is smart enough to figure out what the test set values are. So your comparison is going to be between forecasts and the values in the test set. And again, we see if we compare different metrics column-wise, we see that the lowest values are actually found for the seasonal naive method. So the seasonal naive method in this case, just in this case, is a winner when we were thinking about in-sample fit, and also is the winner when we are looking at forecast accuracy or looking at out of sample fit. So here's a slide that shows you different questions, just true and false. Let's take a look at this first one. Good forecast methods should have normally distributed residuals. True or false? The answer is true. We would want that our residuals behave normally. The second statement says a model with small residuals will give good forecast. Well, not necessarily. We could have an overfitted model that has small residuals but produces bad forecasts. The third thing says the best measure of forecast accuracy is mean absolute percentage error. Well, we don't know if we can calculate mean absolute percentage error for values of y that are 0. So we don't know, okay? There are different measures and they're well suited for different things. If your model doesn't forecast well, you should make it more complicated. Absolutely not. Typically, the simpler models are winners and beat more complicated models. And lastly, always choose the model with the best forecast accuracy as measured on the test set. That is correct. That is true.